Okay, go ahead.
So good morning. It is a great pleasure to welcome Dr. Bini Ouyang from Florida State University to our MUST seminar series. We are currently actually working to form a new project about high entropy materials at Florida State University, and Bing is one of the key people in this project. But obviously, this work is of great interest to the MUST project as well, which is devoted to develop computational methods for similar materials. And so today, Bin will tell us about his work, his computational work, which is devoted to a large extent to high entropy alloys and similar materials. He came to FSU relatively recently from Berkeley, where he was part of one of the major groups in computational chemistry. And so he has some really state-of-the-art ideas and methods that we will share with us today. So without further ado, Bin, you're welcome. The floor is yours.
Yeah, thanks a lot. Let me share my screen first, and I just want to make sure everyone can see the slides.
I think so, yeah.
Yeah, awesome. Yeah, thanks a lot for the invitation. I think it's pretty nice place to summarize a little bit about the topic of high entropy materials, because I just realized it's really a good chance, because if you give a talk in conferences, you typically do not have 1 hour to talk about everything. So I take this as an opportunity to kind of summarize what I have done, actually sort of starting from my postdoc and until what we are doing recently. So that's going to be a combination of several stories. I put a relatively long topic because my group is working on, I started to work on battery materials since my postdoc, and then now we are working on catalysis, and we recently get some funding for high entropy catalysis, as well as I was trained for metal alloys. My bachelor degree is actually in material chemistry and physics. It used to be called metallurgy physics. So it's pretty much about metal alloys. I will also talk a little bit about that. My PhD work is quite related with alloys as well. So the first slide is kind of a summary of what I will cover today, mostly about the first two topics, battery, cathode, and electrolyte. And sort of there's a puzzle why we need to care about high entropy materials for batteries. Is there anything special? It's just some new materials. And all electrocatalysis, this is something we're actively working on. So it's kind of an interesting transition. I will explain the logics behind it. And also I'm going to talk about structural alloys as well. This is what I was trained when I was an undergraduate student. Okay, so let's start with some, I realize a lot of audience may have little background about batteries and what is going on in batteries. So it's kind of interesting because if you look at the battery chemistry, basically the chemical formulas, it has a lot of people working on that and has been developed for quite a long time. But people are still working with very limited elements. So if you have a cell phone, pretty much smartphones using lithium cobalt oxide, or different EVs just have different ratios of nickel, cobalt, and manganese. We call them NMC, which is the first electron of each element. And some of them use aluminum, but only a tiny bit. That's still pretty much nickel and cobalt. This is pretty much all the batteries in the market. Okay, so they have the same structure, which is layered oxide. Quite simple structure. You have alternative lithium layer and transition metal layer. So lithium is going to move through the lithium layer. It sounds like, battery people are not so creative, right? So, I mean, we're working on this kind of thing for like several decades. But there's actually a reason for it. We actually joke it as NMC curse. And the reason for that is because if you want to work in a battery, especially the layered based battery cathode, what's going to happen is like when you move lithium in the lithium layer, there is a chance that the transition metal gonna pass through the tetrahedral bottleneck side and goes to the lithium layer, because you're gonna evacuate lithium layer when the battery is cycled. So this kind of a migration is actually detrimental, majorly due to two reasons. First of all, it's of course obviously going to block lithium diffusion because there's a metal sitting in the middle of the diffusion pathway. And then because those transition metals are typically smaller in ionic radius, so you're going to shrink the height of the lithium layer. That also going to increase the activation barrier. There actually has been quite a bit of work in the battery field to elaborate why this happens and how this happens. And the reason to stop migration, because migration is actually a bad thing, the reason to stop that is quite simple. It's actually in undergraduate courses of chemistry students. It's, crystal orbital theory. Basically, you want to destabilize tetrahedral site and you want to stabilize the octahedral site. That's it. So in that case, your barrier will be super large and hopefully nothing gonna move. So naturally, for choosing an element, you have to fill up all the T2G states. In that case, you have the crystal orbital gap here. In that case, tetrahedral will intrinsically have high energy regardless of how you put the electrons. Very simple theory that result in the NMC curves. If you look at the periodic table, if you have early transition metals, typically we start with 3+ and 4+, they can never have more than 3 electrons. They're mostly less than 3 electrons due to the how many valence electrons they have. So you can never use titanium, vanadium, chromium in those structures. They're going to migrate naturally. And also you have manganese 2 and iron 3 in high spin states. They prefer to form high spin state in metal oxide. They have D5. They're going to occupy all the orbitals I showed here. So in that case, it's the same thing, right? So tetrahedral are going to be similar with octahedral. These 2 ions are also very mobile. So naturally we have manganese, but still manganese 3+ may have some hope, but these 2 are Young-Taylor species. So when you oxidize them, when you reduce them, the Young-Taylor distortion going to change, right? So hopefully the bond length is going to change significantly. So that also going to influences the mechanical stability of the layered structure. So that's actually, eventually you have no other choices. You have to rely on cobalt redox and nickel redox. And manganese 4+ has been used, but you don't want to reduce that in the layered material. So that's actually the reason why people are still working on this limited chemistry. But if you heard about news from like Tesla and EV industry, you're gonna realize, cobalt has some problem in supply chains. And this is actually some screenshot I took a couple of years ago. So a large portion of cobalt coming from a single country in Africa, and it's extremely hard to mine them. And there are all kinds of illegal things going on in that country. And also the cobalt price shoots up very quickly in the past few years. And also nickel is actually not a good substitution. Even though in Tesla, everything moves to high nickel. Every EV company nowadays will chase for high nickel batteries, but nickel is actually just not so cheap. It's almost the second most expensive metal in the 3D, if you forgot about scandium. Okay, chromium, manganese, iron, copper, zinc are all cheaper than nickel. And the nickel price is actually going up continuously. So this is what we are worrying about in battery materials so far. Okay, so we have limited chemistry to play with, and then we have to design some new composition. Hopefully it's cheaper, but also perform better. So I'm going to explain my day one as postdoc. I was not trained in battery in PhD. I was working on 2D materials actually in PhD. So I joined Professor Cedar's group, and in the first week, we have a brainstorm about what we're going to do in terms of material discovery, because Gert Cedar's team was on high throughput material discovery. So I come up with some random idea. So my random idea is related with today's topic. It's a random idea because I have no idea what I'm talking about. I'm just saying, okay, so can we just add more elements so that we have more materials? Hopefully we can screen more, and then maybe we'll find something good. And this is the response of my advisor. It's like, thank you, Beam, but we do not do random things here. Okay, so that's actually the field of high entropy battery looks like about 5 to 6 years ago. I mean, it's kind of an interesting idea. It's new material, but it's sort of random. Like people have no reason to go to high entropy. So we sort of need a reason for that. This actually conclude what I have done, what I have majorly done during my postdoc. So I'm gonna use the later slides to explain to you the logic. But I actually did not start directly with high entropy. My advisor have something more exciting at that time to work on. So to solve this NMC curse, we can use disorder. Okay, so the disorder we use is actually compositional disorder. It's very simple. When you create the mixing between lithium layer and transition metal layer, you're gonna end up with a rock salt structure because they have a coupled FCC cation and anion lattices. When these 2 sublattices mix with each other, it's a rock salt. Otherwise, the layered structure can be regarded as the ordering through the 1-on-1 direction of FCC lattices. So this is called disorder rock salt battery, and hopefully it's actually on the way to be commercialized. So there has been quite a few consortium right now in DOE about this. about also how to commercialize those materials. So this is naturally my first project. And because of the disordering, you don't have to worry about the transition metal migration because there's no layer anymore. So hopefully you don't need to worry about the shrink of layer height. You don't need to worry about the block of lithium pathways because instead the lithium diffusion in this material is rely on some local structure. We call them 0TM unit or sometimes 0TM channel. So if you have lithium with all the first nearest neighboring in this tetrahedral local structure being just the lithium, of course, they can be transition metal in other situations. But if you only have lithium, you can easily do a DFT calculations, and you will find the diffusion barrier is actually much lower than the other local structures. So all you need to do is actually have a lot of these 0TM units in a disordered lattices, and everything start to percolate. And in that case, you're going to hopefully have a good enough diffusivity. That's basically the first idea of designing the so-called disordered rock salt type of lithium cathode. And this is actually the first paper about it. So naturally, when I joined Girls Group is 2018, it's actually 4 years after this paper. So we actually get started in something really strange. So this is two compositions, disordered rock salt structure. Both of them are disordered rock salt. They have the same amount of lithium. The redox center are pretty much the same, manganese 3 to 4. But if you put them into batteries, they behave totally different. Titanium and zirconium are redox inert here. They will not have redox. They are just charge compensator. We need some high valent metals here to compensate the charge. But the capacity differs by 2 times, and they have the same structure. They have the same redox center, same amount of lithium. So we are sort of get confused what is exactly happening. So later when we do characterization, I mean, a simple electron diffraction going to tell you the differences on structures. They have very different diffusive scattering features. The Bragg peaks are exactly the same because they have FCC and also rock salt structure, but they have totally different diffusive scattering features. Those are something called chemical short-range order. It's actually well studied and well observed in alloy systems. Okay, just in case the audience does not have background, I mean, can be explained in a very simple way. So this is essentially the Pell preferences in the lattices. We have the Warren-Coley short-range order parameters. You can easily calculate that if you know the probability of finding B Pelling with A, and you can divide it by the concentration of B. If it's fully random, then in that case, you should get 0 for this parameter. But as long as you do not have 0, you're going to have short range order. That's essentially the definition of it. And it's actually discovered in 1950s, quite a long time ago. And the reason why people derive it in this way is because if you take a Fourier transformation of it, that's actually the analytic intensity that you can see in diffraction, either powder diffraction or electron diffraction. So that's actually a little bit of the background of the short range order features. And then the remaining question for the battery problem is like, we already know that we have a disordered lattices and we have to diffuse through those 0TM units to have low enough activation barrier. And hopefully those 0TM units will form a network, a percolation network, so that lithium can move in this highway. But sort of the question is like how this short range order gonna influences the diffusion network. That's now well-described theoretic problem that we want to solve. Okay, so we spent quite a few years, and as you can see here, this paper actually published this year. So we actually started that in 2018. It's not so easy to get a well-controlled comparison experiment and theory. And I also get frustrated myself a little bit trying to understand what is going on. Because everything is quite simple, Pell preferences, but in reality, it's not just one single Pell. So the Pells gonna mix with each other and form some local structures. And the bulk composition can conserve in those local structures. So those, like the first tetrahedron here is basically a tetrahedron formed by first nearest neighbor cation site. And the E here, which is the octahedron, is a mixture between first neighbor and second neighbor in the FCC lattices. And F is actually second neighbor and the third neighbor atoms in the sublattices. So if you conserve bulk composition is one lithium, one metal in those local structures. And if you can do a Fourier transformation of it, you're going to get very different diffusive scattering features. You just plug that into the equation above, you can simulate that directly. Okay, so you're going to have all kinds of patterns, but some of the pattern match with the experiment. Some of the pattern have never been seen before. So it's kind of a strange. And then we realized because in reality, you have a mixture of different patterns. So we see a lot of this ring before, which this is quite simple. This is widely observed in alloys as well. Many of the alloy, for instance, nickel moly alloys have shown this pattern very frequently. But sometimes we get something like a squirrel-like. So, I mean, there are subtle difficulties. Feel free to zoom in. You can see like the second diffuse scattering feature is less rounded. And this is sort of a puzzle, like what exactly happened to the local structures. But if you start to mix the, let's say this is an octahedral type of short range order with the cube type of short range order, somewhere in the middle, you're actually going to form a diffusive scattering intensities, which is more like squirrel-like. In that case, we have the hypothesis that eventually in this material, we have a mixture of bulk composition in both local structures. And additionally, we can extrapolate that and figure out what are the rest of the diffusive scattering features that we have seen. We can mix the octahedron with also the cube type of short range order or the tetrahedron type of short range order. On the top of the second column, actually at the top one is still the octahedron type of short range order. The bottom one is actually the tetrahedron type of short range order. And you start with a round shape, and in the middle, you're going to have this kind of a diamond-like superlattices. And it looks pretty much like superlattices, but this is actually not long range order. This is short range order in general, but you actually have a spot rather than a diffusive line or something else. And in that case, we kind of
May I ask a question? So
yeah.
this is actually very similar to what you have in certain dense liquids. In liquids, you often have some types of short-range order, and you can see diffuse Bragg peaks. But there's also strong temperature dependence because the kinetics changes. Now, you didn't mention anything about kinetics here. Is this temperature dependent, these patterns, or what?
Yeah, very good question. It's actually definitely temperature dependent. So I'll take these two as example, the round one and the square one. So the square one can be obtained by quenching the materials with different speed.
Mm.
So that means if you limit the kinetics, sometimes some local structure will decrease in population, some local structure will increase. So that's actually the experiment we tried in this paper. So we anneal the material with different time and or we quench it with different rates. And
So,
also it's sort of controlled by the elements as well.
see, so this is in fact very similar to if you have, for example, liquid argon and then you cool it quickly instead of crystallizing, it will form an amorphous glass. But before that happens, first of all, this is a time-dependent phenomenon. Second, there are some Bragg peaks like this, which characterize short-range order. So, has this been studied, the temperature dependence of the diffusion rate, for example, of these elements, of these atoms?
You mean in the disorder rock salt system?
Yeah, for example, has the diffusion constant been measured, or can you measure it as a function of temperature?
So that's a good question. It's not so easy to measure in situ. I think all that matters is actually what happened during the synthesis process or the annealing process. We tried something ex situ. I mean, if you synthesize those materials, you want to match your diffusivity, but that's out of the topic. In situ wise, I'm not sure I'm aware of the experimental techniques that can be measured. But I mean, sounds like you know a lot of this
Well,
tech.
this is normally glasses don't live on a lattice, but this is sort of like a liquid of particles randomly placed on the lattice.
Yep.
And it seems to have this is a similar phenomenon to freezing into amorphous solids. It's just that what that has been studied a lot, and through some scattering experiments, they were able to actually learn a lot about the slow kinetics and various structures, and all of those things have been studied a lot in so-called fragile glass formers. But so I'm trying to see if there is a connection here to this well-studied problem.
Yeah, definitely. Yeah, I do agree that and thanks for letting me know that there are a lot of relevant study in the glass field because typically we are looking for metal alloy papers because it's also a well-studied topic in the metal alloys, especially FCC-based alloys. But I guess now we have a new tool. Yeah, I will definitely check out. I will probably bug you in the future for more references of this.
Yeah, that's very interesting.
Yeah. Thanks a lot. All right. So that's basically coming back to the slides. So we basically kind of figure out that this is kind of a mixture of several of the basic type of local structures. And then the question is like, we are talking about lithium percolation, right? So we have to explain how those local structures gonna influences lithium diffusion. So a typical way people regard short-range order is like is regarded as a remnant of long-range ordered structures. So in that case, a useful way to do that in crystalline materials at least is looking for the long-range order version of those materials. So it's actually not so hard. You just need to search for ICSD and material databases. For instance, if you have this is actually so-called 2TM channels, means like even every single local tetrahedron, you're gonna have 2 lithium, 2 metals. We actually have a known material type like this. It's called the gamma lithium oxide type. It's a low temperature phase of lithium ion oxide and widely exists in a lot of lithium metal oxide system as long as your metal species get large enough. Okay, so and this material is a terrible material in terms of battery because as you can see from the 0TM channel theory, like they have the minimum chance to have 0TM channel. They have 2 lithium and 2 other metals. Even if you have a fluctuation in high temperatures, it's just much harder to get rid of the metal in the local structures. So this is a terrible long-range ordered structure. Second one, when you have bulk composition in the octahedron, it's actually a very neutral one because it exists widely in terms of all kinds of long-range structures, long-range order structures, including layered structures. You're going to see that. Spinel-like structures, you're going to see that. And gamma lithium oxide also have that. Okay, so this is probably because it's no longer the first linear stable interaction. So that means typically we're going to think the interaction strength is going to be a little bit weak. And in that case, it has somehow is more tolerable in a wide range of structures. And the third one is kind of interesting because we didn't find any bulk structure for metal oxide. It's a special layering going on. Instead of layered order in the 1-1 direction of a cubic lattice, you have the layered ordering in the 1-1-0 direction of the layered lattice. But we do find a paper a long time ago talking about the FCC ground state of intermetallics. Okay, so in that case, we found a silver zirconium. There is actually a phase of that having this kind of unconventional layered structure. And because of that, you're going to have bulk composition, which is 1-1 ratio in the cube. Okay, this will slightly increase the chance of 0TM channel. So that means, to make a brief summary, the first one is actually terrible. If you see a lot of this local lithium 2 metal 2, it's going to be a terrible conductor. And if you see the similar patterns, it will be terrible conductor. The one in the middle is kind of neutral. The one on the bottom is actually a little bit better. So that's actually the percolation threshold for those 3 types of short-range order features. Okay, so with this kind of a qualitative understanding, and we kind of map the electron diffractions back into the 3 types of local structures. This is sort of a summary of the previous few slides. The next question is how do we simulate that, right? So ideally, as a computational chemist, we want to predict what's going to happen when you have a certain environment of synthesis and processing. So we're using some tools called the class expansion. It's actually a generalized Ising model. So we assume that the total energy of the system is a summation of the contribution of all local structures, and we just sum it up. So this is essentially a regression problem. So what we need to care about is how many features are really useful here. We have to do some compressive sensing to reduce the amount of features because you can easily end up with 1 million features, which is not really solvable mathematically. And then we have to pick up the right structures and we have to automate the process because every single system will be at least like 1,000 of DFT calculations before we can really have good enough Hamiltonian from class expansion. So that's sort of the idea behind it. I kind of summarized briefly and feel free to ask. We actually have a nice review paper of all the technique details about class expansion. So I spent quite a few years, but now we are at a very good shape of simulating these patterns. So this is my favorite slide to show how useful those simulation tools can be. So those are the 3 experimental diffuser scattering features that we see. And we can basically simulate the same composition, which is the first one is lithium titanium manganese oxide. T means titanium, M means manganese. The second one is actually oxyfluoride. We dope fluorine into the oxygen lattice. Well, the third one is actually the manganese zirconium oxide. So we simulate the same composition as experiment at experimental synthesis temperature, and we do Monte Carlo simulations to sample the disordering configurations, and then we do the Fourier transformation. We're gonna see exactly the same diffusive scattering features. It's not exactly the same. Maybe I over-exaggerate a little bit, but we pretty much capture the shape of the important shape features of the short range orders. That means we can generate more realistic atomic models, and then we can use these models to do some predictions of properties. In addition to electron diffraction, we can also do PDF. So this is another collaboration with a team in Oak Ridge National Lab. It's like at the left, PDF is actually fitted by an average structure, assuming fully random. Sometimes it's actually not working very good. This is actually a fairly good one. 11% is actually not so bad. We actually see some structures even worse, even if they are fully disordered. The random structure doesn't really agree with PDF. So using our Monte Carlo structures, we have reduced this RW quite a bit. And most importantly, we have a Hamiltonian to guide the structure compared with reverse Monte Carlo. Reverse Monte Carlo is kind of widely used in this field to refine structures. But one of the challenges, like sometimes you're gonna go to a structure that physically will not make too much sense simply because different structure can end up with the same PDF pattern. So you want to pick up the right one that's gonna be formed following actually a certain physics rules. So that's actually the demonstration of the fact that we can generate reasonable structure. And naturally, we can use this to predict battery materials. We're coming back to the design problems. So the color map here is actually how many lithium are gonna percolate in a certain composition of lithium manganese oxyfluoride. We want to use manganese, and the whole field of lithium ion battery want to use manganese because it's cheap enough, it's abundant enough, there's no toxic issues. It's sort of the best element after iron. Iron is actually the best element, but it doesn't really work so well due to a lot of other reasons. So we simulate the complete space of lithium manganese oxyfluoride, and now we can map the kinetics of lithium percolation here.
So wait,
I
I just have a question here. So
Sure.
for a given structure, you can generate some structure with Monte Carlo, some configuration of all atoms, and then you can look at how many neighbors, of lithium you have and so forth. You can characterize percolation like this, but this is not necessarily the same as kinetics. Now, to what extent is actually kinetics being measured with Monte Carlo? Because there is kinetic Monte Carlo that people can do as well.
Exactly. So I should probably be more precise here. So this is more like the kinetic network rather than the actual, for instance, diffusivity. But of course, we can do kinetic Monte Carlo simulations to directly simulate the diffusivity, which is also part of something we are doing because we have the Hamiltonian of the lattices, and then we can fit the barrier, and then we can do the kinetic Monte Carlo.
Another question is, you said that you can first do DFT at some level, and then if I understood correctly, correct me if I'm wrong, then you get an effective classical model of charges interacting through some forces. Is that correct? And then you can do Monte Carlo on that classical model of charges with forces.
Yes, then we do Monte Carlo to find the lowest energy or the equilibrium ordering of the charges.
But are these pairwise forces that you get? You didn't say.
Not really. Like typically, that's the idea of a class expansion because the Ising model is like first nearest neighbor pairwise.
Yeah.
But what we can generalize it into any. We call this many body, but I mean real many body physics people will not agree with it. But we have 3 atom interaction, 4 atom interaction, 5 atom.
Of course they are 5. There are multiple atom interactions when you have electrons moving around, right? So that's clear. But to what extent is the interaction long range? I mean, is there, because I think these are not really metallic systems, so the Coulomb interaction is not going to be really screened here. And so to what extent are these interactions of long range? They're the long range, because you're talking about local clusters, these are local configurations, but there is also the issue of long range interactions.
Yes.
So is this included here in this calculation?
Yeah, very good question. So this is sort of the idea of like what is a good cutoff of the interactions. So first of all, I will tell you how we approach this. First, we have EVO summation here. There is a long range term in EVO summation.
Yes, sir.
So in our Hamiltonian, we automatically have EVO summation. In that case, it's included. And then we have the cluster interaction radius. In that case, we have some empirical values. It really depends on the performance of the fitting. So if the fitting arrow converge, we just cut it off there. But it's physically, we're not so sure. For instance, it's gonna decay after fourth nearly stable, fifth nearly stable. We have little idea for now.
See, I wanted to mention that, a lot of work has been done. In fact, we are working on the ordering of electrons at low density conductors, and they form a lattice Wigner crystal. And it is known that because of the long range interaction, these charged crystals are very fragile. So the energy you need to start moving or melting it is very low. Now, of course, here you're not really talking about a crystal of charges. You're talking about a liquid of charges. And so in some sense, it's a little different issue. But what is apparently known is that because of the long-range interaction, this kinetics is actually somewhat faster than it would be for only purely short-range models. So anyway.
Yeah. I sort of get the point, but yeah, I can definitely keep chatting with you on that. Maybe offline. Yeah, I'm very interested in what you see.
Okay, thank you.
Okay, so coming back to the slides, it's like again, this is when as a theoretician, when I am really happy about it's like something we develop and something we propose can work. Okay, so hopefully this actually can be used as a evaluation of the first cycle performance of battery materials. So what we do is like we pick up 6 compositions and then we measure that in experiment about the capacity of those materials. And if our percolation theory works, supposedly we're going to see a decay of capacities from sample 1 to sample 6. And we do see that in experiments. So that gives us a little bit of confidence of using this model. And as Vlad mentioned, it's not real kinetics. It's more like a network analysis, but it kind of rings a bell. It will still be useful for guiding our experiments. And then as a computational people, the next thing we do is like, why don't we just scale up, right? So simulation is typically cheaper than experiment. So how do we just span it into more spaces with cheap metals? And hopefully we want to look for good materials. So we generate a bunch of these percolation maps across typical chemistries like nickel and manganese. And we sort of found something really interesting because the dashed line here is a random limit. This is assuming you have no short-range order. We sort of realize it's always the case that the real percolating amount of lithium is lower than the short-range order. This is actually different from the first paper, if you still remember, in 2014. My advisors group has a science paper. Assuming everything is random, then this material is going to work. But we sort of realize it's not random at all. It's actually quite below the random limit. So the question then has been switched into how do we maximize the randomness of the lattices to get rid of this short-range order because it looks like a bad thing. As you can see here, unless you have a high enough fluorine concentration. But if you do synthetic chemistry, you will know that putting fluorine into oxide is super difficult. So it's not so easy to dope 30% of fluorine. You need high energy ball milling for like 100 hours or something like that. It can never be scaled up. So we struggled quite a bit here at that time, and we spent about 1.5 years trying to dope fluorine into the system. It doesn't really work out very successfully. So the question is like, do we have other ways of doing random? Okay, so this is when I start to talk about high entropy. Okay, so because at that time I had a friend in Berkeley working with Professor Andy Miner and Professor Mark Astor. They're talking about something really interesting. So they are arguing about if there's short-range order in high entropy alloy. So this is a Nature paper published at that time. They use energy filter TM, very special experiment, and they need very special equipment to visualize those diffusive scattering features in medium entropy alloy. It's not even high entropy. They only have equal mole of 3 elements. And they get very excited because eventually they think they found the evidences, firm evidences that short-range order indeed exists. So people are kind of arguing about it. This kind of inspired me quite a bit because the fact that people need to argue means at least it's not obvious. I cannot say if it exists or not because I'm not expert in that field, but it's not so obvious. This is exactly what we want, right? So we want to get rid of short-range order. So why don't we just put more metals into it and make it high entropy? If we work the same way in a rock salt system, they are also FCC, by the way. So we're probably going to get rid of the short-range order. So because of that, we did high throughput screening immediately and looking for what can be more disordered. I don't show all the details here, but just to let you know how many materials we tried. It's pretty much all the chemistries that battery people want to try. And we come up with these four chemical formulas with 4 transition metal, 6 transition metal, just want to make it high entropy enough. And the first thing we do is electron diffraction, and we do see that as 2 transition metal, you're going to have short range order features, but as you gradually add metal into it, the short range order feature going to disappear. I would not argue that it's totally disappeared. This is still unsolved question in the field of alloy, but I mean, at least you cannot see that very obviously. That's good enough for us. Okay, so then we tested them as batteries. Okay, so we make them into batteries. They have almost the same theoretic capacity, but the real capacity electrochemically actually differs quite a bit. But this is still not the end, because sometimes you just get the right result with wrong reasons, right? So we have some hypotheses and it works, but it works due to totally different reasons. We argue about kinetics. We have to verify that the kinetics is better. Right, so the way to do that in battery is very simple. You just cycle them in different current rate. If you have a poor diffusivity like 2 TM, like if you cycle that at very high current rate, like 2 ampere per gram, the capacity shrinks quite a bit to about 50 milliampere hour per gram. It's a significant drop from the right-hand side to the left-hand side. But for the 6 transition metal, you can still maintain about 180 milliampere hour per gram. This is actually what we are using right now in a commercialized battery. But instead of charging that for a few hours, you only need to charge that in 10 minutes to reach the full capacity of, like, if you're driving a Tesla, hopefully you're using NCA cathode. So this is just sort of a comparison.
Incredible.
And the cool thing is, like, it's cheap enough. Okay, so it has 5% of a cobalt. We didn't get rid of a cobalt yet, but we're working on that. But the rest of the elements are just cheap metals. We do not have any nickel here. And we minimize the cobalt to be 5% because we still need to put some elements. We only have so much metals in periodic table. That's another issue. So this is actually the end of the cathode part. Like my advisor's kind of a change. I kind of joke a little bit about this. So he changed the thank you beam. We don't do random things here. Eventually he said, okay, that's great. Let's submit to Nature Materials. So that's actually the story happened in my first stage of a postdoc. It's actually eventually become my own research as well, because we get funded at FSU from Samsung SDI. They read my paper in postdoc and they come and talk with me. And we are actually working with Samsung in FSU for 2 years on trying to commercialize those high entropy batteries. And there are, of course, a lot of problems that is not solved. Okay, so now I'm going to switch topic, but still about batteries, but it's more about general inferences of diffusion about disordering. It's actually a bad thing. Vlad is an expert in Anderson localization, as I realize. I mean, there has been a very famous paper from Dr. Philip Anderson saying that, be careful about random lattices. It's sometimes really bad for diffusion. It's about electron transport mostly, but the similar idea can also apply to charge transport, like simply diffusion, if you are from material science. So in the very beginning, we try to agree with this theory because we sort of realize it's indeed a bad thing. Think about the diffusion, right? So this is the diffusion you see in the textbook. You have a crystal lattices, you have well-defined first nearest neighbors, so your local environment are kind of fluctuating periodically. You're going to have some diffusion barrier. That's the diffusion mechanism, and that's essentially how you calculate diffusivity. But when you have a disordering, the local environment, even though it's still crystalline, you have compositional disorder, the local environment is going to fluctuate quite a bit randomly. And in that case, you have some kind of a wiggled energy landscape. And there's no fixed diffusion barrier anymore. So there are infinite amount of diffusion barrier, really depending on the local environment. If you consider long range interaction, that's definitely infinite. But if you only consider short range, there's still a lot of choices.
Did you try to calculate the distribution for barriers? If you look at local sites in the crystal, then each site in an alloy will have a different barrier, say, but you can do a histogram and you can try to characterize the distribution functions. So
yeah, exactly. Yeah. Yeah, exactly. You're absolutely right. We actually can also do class expansion on that. I didn't cover in these slides, but we are doing that. So we can fit the diffusion barrier as a function of local environment. Yeah, so this is sort of like what you said, we can fit the histogram in a reasonably accurate way. Yeah. Okay, so but I mean, this is a picture that actually frustrated us quite a bit because we actually start to write a paper to disprove that, high entropy alloy may only work for limited chemistry like disorder oxide. Otherwise, it's not a good thing. Think about the Anderson localization. So the reason the reason behind it is even if you have
Wait a minute. I mean, Anderson localization, this is a wave phenomenon. It's a wave interference phenomenon, which for classical particles that cannot happen. This is
yes.
it's a little bit different than the difficult diffusion in dense liquids and so forth. There are very different reasons, but I think Anderson localization is a quantum. I don't think you can talk about a quantum effects for moving ions or atoms.
Yeah, I totally agree with you. Yeah, that's definitely correct. So that's why I need this slides to explain that in classic diffusion. So it's still a bad thing if you look at the diffusion equations, Arrhenius equation in this way. So whenever you have a local minimum in the energy landscape, you actually create a localized trapping state. It's not trapping state like electron transport, but the ions just does not want to move out because they intrinsically have a large barrier to jump out. So this is gonna cause the losing of carrier concentrations because some of the carrier just doesn't want to move. They are in local minimum, and it's extremely hard to move them out. So in that case, you're gonna have a small prefactor in diffusion. So this is actually regarded as something bad. When you form a distribution, some of the part of the distribution is actually good, some of the part are actually bad.
Yes.
So we get very disappointed in that case. In that way, we actually write a paper. The paper is also published and recently that we should be careful about disordering. It's actually bad for diffusion. And if you go to high entropy alloy field, 4 fingerprint of high entropy alloy, one of them is sluggish kinetics. People just think, high entropy alloy is going to have slow kinetics intuitively. So in that case, but then we realize, it's not always like that. Diffusion is not an average property. You don't have to average the diffusion barrier to calculate diffusivity. As long as you have a low energy diffusion channels, you can reduce the diffusion barrier. In that case, it goes exponentially. So this is kind of a trade-off. You lose some carrier concentration, but other carriers can diffuse in much lower barrier. If eventually you still have the chance to have high enough diffusivity. So that's actually something we found later, and then we just want to verify how much tunable space we can have in real materials. So we pick up, and before that, let me introduce how we consider diffusion barrier. This is also falls back to the suggestions that Vlad indicates. So in a frustrated energy landscape, we have all kinds of diffusion barriers, but typically we decompose that into 2 parts. Well, the first part is side energy differences. This is the intrinsic barrier. This can be calculated by any Hamiltonian like class expansion, for instance, directly. And then all we need to do is actually to fit the kinetic resolved barrier. This is a kind of a relative energy at the transition state. So if you have enough of this barrier information, you can fit that as a function of local environment, just like class expansion. So, and this also tells us another story that in some of the older materials, if your side energy difference is really large, there is basically no hope to make it better because this is the intrinsic barrier. It doesn't really need to care about what is a KRA is. So as long as you have large enough side energy difference, diffusivity is by definition low. But for disordered materials, this is a different story because you're going to form a distribution, as Vlad mentioned. So if you can control the distribution and make them overlap, in that case, there is a chance that the percolation gonna happen in the overlapped region. So now the question is, how do we introduce this overlap? So we pick a well-studied system for ionic conductors. It's called NASICON. It's basically polyanion systems based on phosphate and silicate with a sodium or lithium and with a metal. So in these materials, a very obvious ordering going to happen between the 6B side and 18E side. They have very different coordination number. 6B side is an octahedral site, and 18E side is heavily coordinated side. So this is why they have ordering, because the chemical bonding environment are totally different. And we can easily calculate the side energy differences, taking one example, like sodium zirconium phosphate. side energy difference is like 0.85 eV, which is pretty large for superionic conductors. It's not even good enough for high temperature fuel cell, because in that case, we need something like 0.5, 0.6 eV. For superionic conductor, for batteries at room temperature, you need something like 300 MeV, like 0.3. But if you introduce disorder, here we want to do control experiments. So we don't want to replace elements, because people are going to argue that, okay, you have different electronic structures, have different radius. It's not a controlled experiment. So what we do is like, we just introduce a perturbation of the bond length. In that case, we are imitating the distortion introduced by forming solid solution. And we use a standard deviation of 0.1 Armstrong. In that case, this is something that we can reach, because ionic radius doesn't differ that much in general for cation species. And as a result of that, we introduce the bond distortion. We reduce the DFT calculations in the disordered lattices and calculate the side energy differences. And now we form a distribution. So the 6B side is going to overlap quite well with 18E side. And a lot of them overlap in the window of 0.85, which means some of the nearest neighbor are going to have low enough energy differences. And our hope is that they can connect with each other and form a percolation pathway. So we did some percolation analysis. So the axis basically the threshold of nearest neighbor energy that we allow, which is the side energy difference. The Y is actually how many lithium and sodium can percolate in this way. If you have a fully ordered, you have to reach 0.85, because it's all the lattices. You have to be larger than the side energy differences. But if you have disordering at C point, 22% of sodium will start to percolate with 0.14 EV, which is low enough barrier. We're looking for something like 0.3. So 0.14 is good enough. And then if you can allow a little bit larger, like 0.5, half of the sodium will actually percolate. So you eventually lose kind of roughly like half of the carrier concentration, but you gain a lot by taking exponential of the lower down of the activation barrier. So we sort of prove, at least for the sodium nasicon structure, distortion gonna help percolation at much lower side energy differences. And then we try to generalize it in other structures. Lithium nasicon, this is a lithium version of the same materials. We also did lithium garnet, so which is totally different structures. It's intrinsically a silicated mineral, but battery people successfully make them into very useful superionic conductors. So for all cases, the distortion, we did the same calculation by introducing perturbation of the bond length. They all can cause different level of overlap of side energy difference, side energies. And then you're going to start to percolate lithium at much lower diffusion barriers. So this is sort of a generic phenomenon, regardless of which acclimato you have or which lattices you have. And then we get experimental verifications. You know, experiments. In experiment, we cannot just perturbate the lattice. So we have to introduce the lattice by elements. So this is actually sort of the reason why we need to go high entropy, because entropy going to help us to stabilize ions with very different ionic radius. If they have the same radius, it's actually not something we show in the theory, right? So that's why we want to put equal mole concentration of all the 4+, or for instance, all the 3+ real earths and all the 6+, as you see in the third column of the data. So we make those high entropy version equal molar ratio of each metals, and they show very reasonable ionic conductivity. And most importantly, they actually the conductivity is actually higher than any of the low entropy counterparts. So this is more important.
Can you just say by how much it it improves?
Orders of magnitude. This is this is log 10.
Yes, I didn't look at the scale. I say
Yeah.
you can get a factor of even 10 or more.
Yeah, exactly. Because I totally I think that that's a very good point. I really appreciate you looking at that, because in solid state experiment, the arrow bar of connectivity is quite large. So we need to be aware of that. So orders of magnitude is actually more convincing than I just increase the connectivity by 2 times. Because 2 students working on the same condition can generate that kind of range. So that's something we should be careful. Yeah, and another important thing is also it's not a linear combination. So a lot of things happening in the high entropy field is like effectively we just mixing 2 properties or 4 properties together. We get an average property out of it. But I think the exciting part is like it's actually higher than any of the single metal compound, which means it's not really something like you're just mixing properties in a single phase. So that's another highlight I just want to mention here. Okay, so and the last thing is basically when we enjoy the discovery, like we try to optimize the conductivity, push the limit, and this is just a demonstration that we can really challenge the record of superionic conductors. 3 millisiemens per centimeter for metal oxide is actually pretty good. It's commercialized level, and we made a bunch of them here. So with more than at least 1 millisiemens per centimeter, which is more than enough ionic conductivity for superionic conductors, just to give you a sense. But this space is largely unexplored. Okay, so and regardless of what other chemistries can be made and what other chemistry can be better, we still have very limited understanding. This is also something we'll continue to work on. Okay, so that's pretty much, and as you probably see, this is actually the interface when I already joined FSU because we're wrapping up this understanding. And as a first-year assistant professor, when I joined FSU, I was thinking, okay, I have to do something different. I cannot just do the same thing as my postdoc. So I have to transfer this idea, something I'm good at, into a different field. So then I realized, this overlap idea can be applied into catalysis as well. Okay, so now we start to talk a little bit about electron structure, but not electron transport. Because one fact for catalysis is that we're looking for optimum surface site that have the right electronic structure, because that's going to contribute to the right hybridization with molecules. And that's going to contribute to the absorption energy we're calling about. And naturally goes to the over potential of using them in catalytic reaction. The fact is that sometimes we have to stick with noble metal. And the reason is kind of similar because noble metal just have the right electronic structure, for instance, d-band center, or for instance, other features of the shapes of density of state. And if you use cheap metal, it just doesn't want to go there, electron-wise. So there I'm thinking that maybe we can use the same trick, right? So why don't we just introduce disorder? They're going to form a distribution of electronic structures, and we have the hope that some of them are going to reach into the optimum region. In that case, we can do chip catalysis using cheap metals, and part of them going to behave like noble metals. So we actually write this as a proposal, and this is actually a proof of concept result. This is the medium entropy alloys with no noble metal. Effectively, this is the distribution of d-band center, because people use that as a sort of a metric to evaluate how good they are in terms of HER and OER. So naturally, you're going to form a distribution because of this ordering. They overlap quite well with platinum 111, which is used for HER, and copper 111, which is used for CO2 reduction. So that's basically a sign that cheap metal can work if you make them into disordered materials. And we actually recently got funded by ACSPRF. There are a couple of manuscripts under preparation. So I'm going to show just some of the preliminary work rather than directly jump into how catalysis work. We still don't know that, but we are working on it. Okay, so some of the preliminary work is, the first question is like, how do we can even synthesize those materials, right? So because if you develop a fancy composition that is promising computationally, and then you talk with the synthetic people, they said, okay, I don't want to make it. It's impossible. We cannot even have the precursor sometimes. So the first problem I want to solve is that, can we understand a little bit better of the synthetic accessibility? If we choose any random metal from the periodic table, hopefully some cheap ones, which phase is gonna form, first of all? Secondly, like whether we can make it by using solid state reaction or aqueous reaction or some other reactions that people can use. So this is actually the first independent work we did 2 years ago. So we said, why don't we just calculate all of them? Okay, so I'm a high throughput guy. So the first thing I'm gonna think about is whether we need to high throughput calculate all the combinations. So we calculate a little bit about the throughput. We have 28 metals. Those are the typical metals. We get rid of some of the liquid metals, radioactive metals, and also the toxic metals, because I don't think people are going to enjoy that in the field of catalysis. And then we end up with those numbers, depends on how many elements you want. It's not quite a lot. And if you have to multiply by three for the total amount, because you have BCC, FCC, and HCP, typically as elemental phases. Of course, manganese and tin have relatively more complicated structure in room temperature. The rest of the metals are pretty much one of these three structures. Okay, so we calculate all of them, and eventually we end up with a very large database. The number is actually bigger than this. This is actually some of my old slides, but we're looking at something like, between like 150,000 to 200,000, because our computer is running every day, and I really appreciate we have people from PSC and TACC. Really, I just want to acknowledge that we really benefit a lot from those resources as well. Okay, so, and we finished all the calculations so far, and the first question we want to understand is like, can we withdraw some new knowledge to the phase selections of high entropy alloys? One interesting phenomenon we saw is actually even at DFT relaxation, the y-axis here is actually all the vertical axis is actually what are the phase we initialize. We initialize as HCP, FCC, or BCC. But some of them actually after relaxation going to directly transform into other structure. For instance, BCC going to transform into FCC, even with relaxation. That means it's not mechanically stable at, even like for some of these structures. And they will sort of want to understand a little bit what exactly happened. We don't do any barrier calculation. This is hopefully will be barrierless. Okay, so, and then I need to recall something I learned in alloys and metallurgy. So the BCC FCC transition is well known. It's band transformations because you don't need diffusion at all. You just need to shrink the lattice a little bit. So you can have a BCT structure, it's the body-centered tetragonal structure out of the FCC lattices. Because you have a high entropy, so you're always gonna have all lattice distortions. And somehow if that happens in a good way, you end up with actually more like BCC structure rather than FCC structure. This is why after relaxation, we initialize with FCC, and then the DFT gonna optimize the force and the positions, and eventually gonna figure out that actually BCC arrangement is more energy favorable. You don't need any barrier to overcome this process. It's basically following the relaxation of the force. Okay, so this is actually diffusionless transformation, just like the modern side transformation in steers, right? So this is a well-known phenomenon. And in terms of FCC and HCP, we see zero structures transform from FCC to HCP. I need to go back to this heat map. As you can see, we have 2 0 here. None of the structure are going to transform after relaxation to HCP. And this is because this kind of a transformation need diffusion because they are both close packed structures. The only differences are actually the stacking sequences. So you have to move collectively multiple layers. There's no way that you can do that without diffusion barrier. There's always a stacking fold energy you have to overcome. So because of that, we cannot see that in relaxation. But in reality, this can happen if you have a temperature, and some of the diffusion barrier will actually be quite low. So this is technically going to happen, but will not happen in the DFT calculations. So this is another remark we want to make. And then the BCC to HCP is kind of interesting because it's not a band transformation. You still have to slide a little bit after you take another shape of the supercell. But one cool thing is like the sliding is much smaller. It's actually square root of 3 divided by 6 multiplied the lattice constant. So if you have large enough distortion, this is actually neglectable because everything is off lattice. So this kind of differences sometimes can be dissolved into the noise of the lattice distortion. So that's actually the reason why we see some of the BCC directly transforming into HCP without any barriers because it's DFT relaxation. We're not supposed to overcome any diffusion barrier here. So that's actually the first interpretation of our data because we started with these 3 phases, but a lot of them actually does not end up with the initial phases. Some of them actually relax into amorphous or other structures due to different kind of reasons. And then the second question is like, now we have this kind of a distribution of all kinds of phases. So can we predict which phase you're going to form, right? So we have, if you think about the mechanical properties, right? So if you need plasticity, typically you prefer FCC rather than BCC because you just have more slit systems. Dislocation are more like mobile in those systems. But when you mix random alloy elements together, you are not so sure whether you're going to form FCC or not. So as a theoretician, I'm trying to think, can we predict that to really free, you know, synthetic people out of the combinatorial experiment? So we have the complete data set, which is good news. It's an equal mole ratio of all the combinations among 28 metals. So we're trying to come up with some phenomenological theory. Okay, so, but before I show you the phenomenological theory, we can at least qualitatively see some interesting trend. So this triangle tells you the final ground state after you mix metals with different preferences for elemental phases. So the top here is when you mix 4 BCC metals. It's kind of interesting. If you mix BCC metals, you're only going to end up with BCC high entropy alloys. There's no exceptions here. But if you step down, for instance, to the left bottom, you see eventually when you replace one BCC with FCC metals, any of them, and because you have 315 choices of doing that, and also by replacing 2, if you further step down all the way to where you use only FCC metals. As you can see here, now we have more diverse colors in the circle, simply because even if you fix 4 FCC metals, sometimes you're going to form HCP. And in a lot of situations, you're going to actually form something else. It's going to be a different crystal structure, going to be amorphous phase sometimes. Okay, so this is really intriguing because BCC story is so simple, but the rest of them are actually so confusing. So we definitely need a quantitative model to help us to predict. So before I introduce our model, I want to introduce valence electron concentrations. This is widely used, so far the best model to predict which phase you're going to form. So all you need to do is to calculate how many valence electrons you have. That's why it's called valence electron concentration. If you have a low valence electron, you're going to form BCC. Otherwise, you're going to have FCC. All you need to know is the boundary of it. And from our data set, you can easily figure out the boundary. But the problem is like, it doesn't really work for HCP. As you can see, the HCP at the yellow point, they overlap quite a bit with FCC metals, which makes that if you use VEC to predict FCC with HCP, you're going to have a very bad luck. And this is actually even a worse situation for catalysis because of the noble metal. A lot of these noble metals actually take HCP structures. Very likely they're going to form HCP nanoparticles. And this is going to make things more complicated in that catalysis point of view. So then we decided to come up with something better. And it's actually not so easy to come up with a phenomenological model, but there are actually tools available. So there's something called symbolic machine learning. So what we can do is to come up with a mathematical formula. But there are infinite combinations of what you can use, like basic features and all kinds of mathematical operators. So this is going to end up with a pool of even considering one-dimensional descriptors because it's simple enough for people to use. And you're going to come up with like 100 million of possibilities. And then what we need to do is actually do some sort of a feature selection. This is actually called show independent screening. It's well developed a branch of machine learning, actually in addition to deep learning. This is a cool physics involved machine learning. I would like to call it in that way. And then we can pick up the best model. Now it comes with a mathematical formula, so we can try to understand whether this makes more sense or not. Another remark here is like a typical question is like, how about the unit? You're summing up something with very different units, right? So the trick we play here is like we make it dimensionless by normalize that with a reference electron activity or reference valence electron concentration or reference whatever. In that case, all the numbers here does not have a unit, so you can sum them up, you can divide them. So from this formula, you can see that, well, all you need is also the valence electron concentration, but I also need electron activity, which you can easily obtain from any kind of handbook of material science. And in that case, this new physics factor tau here can effectively separate HCP with FCC now. So HCP is sort of in the middle, and still you have BCC on the left-hand side and FCC on the right-hand side. And it's reasonably good. It's not perfect, of course, but it's actually much better compared with the widely used valence electron concentration. So at least we push a little bit forward of the problem of phase selections. So this is sort of like the first story that we have. And then we're also trying to challenge ourselves. The rest of the world of machine learning is actually trying to build up foundation models. We actually have some cool stuff ongoing, but I'm only going to show part of them, partly because of the time limit. Also, a lot of them are under review right now, so it's not published yet. So, but I just want to show this. This is actually available in archive already. So we can really reach a very high accuracy by using graph neural network, state-of-the-art neural network. The mean absolute error is like 4 MeV per atom. Think about the KBT at room temperature is like 26 MeV. So this is pretty much well below that, which means it's gonna be useful for predicting different the energy difference of different short range order state, for instance, which is a big chunk of this field. And we also actually have a physical model out of it, which is kind of interesting because what I can share with you here is like these 3 models have very different complexity. The first one is very simple. This is actually the simplest model you can go with for graph neural network. The right-hand side is the most complicated model you can go with, one of the most complicated model you can go with. But it does not really change the prediction error. So this actually inspired us that there are some simple physics behind it. And we are able to find out actually the simple physics, which hopefully stay tuned for our research. You're probably going to know what we have done on that. So this is also something I really like. It's like instead of a blindness machine learning, we always need to think about the domain knowledge, the physics picture of what is going on here. And sometimes you're going to get some unexpected reward out of it. Okay, so in the very end, I just want to advertise a little bit. We're building up databases for high entropy materials. As you probably realize, I'm a big fan of doing high entropy of everything. So, and one opportunity I saw as well is that everyone else, most of the other people are trying to calculate everything. I mean, this is a plausible ambition if you have an infinite amount of resources. And this is very useful, will be very impactful if you have a ChatGPT for materials, for instance. But I also realized that for specific, material scientists, for instance, especially experimentalists, they care about only the materials that they're working on, right? So, but in reality, it's like those generic databases have very limited materials for a specific domain. They have a lot of like maybe 1 million materials across ICSD, but if you talk about high entropy alloy, surprisingly, there is zero data, for instance, in materials project. OQMD have a little bit of it. It's a database in Northwestern. AFRO, they have a tiny bit of medium entropy alloys and a little bit of high entropy alloys, but they are pretty much in high entropy carbide, from my knowledge. So when you talk about high entropy battery materials, high entropy catalysis, there is no data available in this field. So this drives me to build up a data set. We call it HelenMD. It's a cool name. It's the god of the beauty, but also is abbreviation for high entropy alloy and energy materials databases. And so far, we have 200,000 of DFT data already. So this amount of data is equivalent to the amount of data in these three major databases. But instead of covering everything, we're covering a small but also important enough field. So we are very rich in data in that domain if you care about high entropy materials. So we also care about mechanical properties, but recently we are kind of working a little bit more on the catalysis and battery part, but just want to show some of the early work I did before. So because mechanical property is actually more promising for alloys, there are a lot of existing benefit here. People kind of understand it much better compared with metal oxide for catalysis or especially for batteries. So I have been working with Professor Taigan from University of Tennessee like a couple of years ago for, at that time, refractory high entropy alloy is kind of interesting. People want to understand what's happening when you have the interstitial impurities like oxygen and nitrogen in the refractory metal alloys. We calculate the ideal shear strength. My PhD advisor is actually doing solid mechanics, so I end up doing a lot of calculations on stacking for the dislocation and grain boundaries, etc. So the next figure is example of actually dislocation pileup. This is actually nickel alloys. It's not high entropy. But the cool thing is like now we have a global force field, as you can see in the database. We're developing a universal force field that enables us to do MD simulation on kind of hopefully a broad range of chemical potentials of high entropy alloys. And then we can study things like, dislocation, motion, also the motion of grain boundaries, and also hydrogen embrittlement. Hydrogen diffusion is a big thing in terms of corrosion of alloy systems as well as high entropy alloys. This is something we're interested in. We're trying to start some preliminary work. So stay tuned for that and feel free to talk with me if anyone is interested, because I realize some of our audience may be more interested in high entropy alloys. That's pretty much about my presentation. So that's my team right now. And I would like to acknowledge computing resources as well. So all the Pittsburgh and Texas resources actually accessed through the Access program funded by NSF. Also, we have resources from several national labs in FSU as well. And that's pretty much about my presentation. I think that's the end of the slides. And if there's any questions, I know this is mostly like a recording, but just in case if there's any questions.
Well, thank you very much, Ben. This was very exciting. results in many directions for future. So are there any other questions that anyone wants to ask?
Yeah, I guess I'll raise a question, and I'm from a DFT background, and I'm just curious. I guess when you build this, you do a lot of high throughput calculations to generate data, right? So, some materials, I guess, has a strong correlation effects. How do you take into account in that in the DFT calculations? Do you use consistent like a density functionals, or use different materials, different density functionals? They could give you different energies, it turns out. And how do you take care of the strong correlation effects for some elements? Like especially when you have oxides.
I see.
So how do you consider that in your actual high throughput calculations?
I see. That's a very good question, and maybe I can provide these two information. So, first of all, we kind of benefit with the fact that battery people doesn't like element with a strong correlation effect. So,
Oh.
yeah, because heavy element gonna lower down the energy density of the battery materials. So typically we just deal with 3D elements and sometimes a little bit of 4D elements. So in that case, hopefully, there is less strong correlation. In fact, from my knowledge, I'm totally not expert on that field. So we never use, for instance, the F block elements. This is something that people like. And in high entropy alloys, also at the same time, for catalysis, we need noble metal, which they are not oxidized or reduced in any way. So in general, I think, some people even use LDA for alloy systems. It's not that terrible. So I would say GGA will be reasonable. And for GGA and for metal oxide, there is indeed a concern because, for instance, a good example is like formation energy of metal oxide is not well captured by GGA. So what we do is like we benchmark the experimental formation energy of metal oxide with experimental values, because all we care about is more like synthesis in the very beginning. So we want to make sure the stability prediction is reliable. So we benchmark through the formation energy. And that's the first thing I want to provide. The second thing is like now we are also working on meta GGAs. We spent quite a few years collaborating with and also talk with experts in this field like Professor John Purdue and also his student Jianwei Sun at Tulane University. He's actually the developer of R2 Scan. So we actually, part of our database is based on R2 Scan actually, because it's effectively going to solve the problem of the formation energy without any correction, because plus U sometimes is a little bit sketchy, it's kind of system dependent, and it's kind of a fitting empirical parameter which deviate a little bit from the idea of first principle. So R2 Scan can really reproduce, at least in the system we care about, can really reproduce formation entropy. So part of our databases are actually built on R2 Scan as well.
Well, what I'm confused about, can you just explain? I mean, for many oxides are actually insulators, whereas DFT, standard DFT will give them to be metals. And so how is this done? I mean, normally people have, as you said, they put U, right? But I would assume that even not that they assume that we actually worked on this, that for oxides like iron monoxide, nickel monoxide, magnesium, the ground state, the lowest energy state structure is wrong if you just do DFT. For example, it will be rock salt for FEO, and DFT will give you something like zinc blend. So how does that enter in your database?
Yeah, that's a very good question, right? So one thing is that the DFT plus U gonna solve part of the issue as I just mentioned. So for instance, nickel oxide, the ground state is actually incorrectly predicted if you just run GGA. And gonna somehow prefers nickel peroxide, which is really strange to people in this field. But if you add the correct U correction, it actually gonna resolve this problem eventually. And another choice, as I mentioned, is like R2 Scan. We actually have a benchmark paper published a few years ago that we try to really calculate the ground state of a typical binary oxide with R2 Scan compiled with what people see in experiments. I think most of them can be correctly captured by the R2 Scan functional. So end up when you build up a databases, if we have these special elements or special stoichiometries, we're going to go to R2 scan instead of just using GGA.
I'm not convinced that R2 scan can solve. I mean, like most of these oxides are moto oxides with localized magnetic moments, and you know, you don't. This is not this kind of magnetism is not something DFT can give you usually. But putting this aside, I actually have another question for you.
Yeah.
When you spoke about catalysis, you said that the surface features like some steps or features in the surface can be very useful for catalysis. My question is, you know, you showed how you have a very large throughput calculation with DFT. I assume that then you don't actually consider chemical short range order, but you just randomly mix them and then look at the stability of the ground state structures. But how do you think that a chemical short range order is actually important for catalysis? What's your feeling about that?
Definitely. That's a very good question. So the reason why we don't consider it is just because we have limited time for now, right? So I just started this research. So the idea here, the big picture here is like, you know, the first thing we want to solve is that we want to have more like a high level picture of how elements behave.
Mm-hmm.
And then we sort of narrow down into a certain subspace.
Mm-hmm.
And this is when short range order going to chip in, because short range order need more detailed calculations and also more detailed comparison, which is system dependent. This is definitely under our radar. This is something we're working on, but we just don't have any result to show here.
Right.
Yeah.
Very good. It's very, very impressive what you do. I mean, I personally have a lot of questions that we'll talk about in private. Like, you know, one of the main issues is that in many of the physical pictures or material science pictures that you describe, there's a sort of percolation, and one ion moves, everything else is not moving. But it's actually very likely that because these are interacting through some Coulomb forces or more complicated forces, that you can't really separate the motion of one atom or one ion from another ion, and that there's some kind of collective motion. Like, you know, most dense liquids, this is what you have, right? And, you know, it's actually sort of interesting. One thing that rings a bell is that in some, they call them Coulomb liquid systems with long-range interactions on a lattice, they found that actually there is this phenomenon that a fraction of even though you have the same species, but because of random environment, some of them can be very mobile and others can be practically not moving. And then there are these two groups, and and understanding, you know, how many in one, how many in the other group. Well, that's I think an interesting question. I don't think has been solved, but maybe has a relevance here as well.
Yeah, definitely. Yeah, I think I recall that you mentioned something relevant in our internal meeting as well. So I'm very interested to hear more about it.
I think that's great. So thank you so much. Are there any other questions? If not, let's just thank Ben once more. And so I guess we can stop the recording. This will go on YouTube, and then hopefully more people will be listening to this talk, and maybe we'll contact you and then the rest of us with questions. So
yeah, definitely. Feel free to contact me.